Hello and welcome to our next lesson in Unit 6. Today's lesson will focus on bonding. There are a few different types of bonding, but today's video is going to focus on ionic bonding. So by the end of today's lesson, you should be able to describe what ionic bonding is and also be able to determine the type of bond that occurs between two different atoms. Now we know that this is a little bit of a review. We've mentioned this before, but chemical bonds result from competition for valence electrons between two different atoms. So the electrons themselves are what are responsible for the bond, and they're what hold atoms together to make different compounds, whether they're made with different atoms or the same atoms. And then they are also what are broken when compounds are decomposed back into their original elements. And depending on the attraction for electrons, which we know as electronegativity, that's going to determine what type of bond we actually have. Now this lesson is going to include three different types of bonds: ionic bonds, polar covalent bonds, and non-polar covalent bonds. But today, we're just going to be focusing on specifically ionic bonds. Now specifically, ionic bonding is going to occur between a metal atom and a non-metal atom. And depending on where that element is on the table, it's going to like to gain or lose electrons in order to form that stable octet. Remember, that's 8 valence electrons in the outer shell of the atom. Remember, metals like to lose electrons. That's called oxidation. So metals oxidize and become positively charged. And we call those positively charged particles cations. The non-metal atom is going to gain electrons, which we call reduction. The non-metal is going to be reduced and become a negatively charged anion. And when this happens, because we have an actual exchange of a charged particle, one atom is losing a charged particle, a negatively charged electron, and one is gaining that negatively charged electron, we're going to create two differently charged particles, one positive and one negative. And we know that opposites attract, so these two oppositely charged ions are going to be very weakly attracted to each other because of that exchange of electrons. And this is what we call an ionic bond. Now this bond can simply be broken by melting or dissolving in water, so it's not a particularly strong bond. Now, as I had mentioned, bonding is all about differences in the attraction for electrons, which is electronegativity, and we can find those values on table S. Now, we'll get into this more specifically with a graphic in our next lesson, but for now, we can determine that ionic bonds are going to be created by elements that have an electronegativity difference, or an END, above 1.7. This number is going to have to be memorized. So if we look at the electronegativity difference of two bonding elements and it's above 1.7, then the atom that has the higher electronegativity, or the higher attraction for that electron, has enough of a pull to actually take and remove the electron from the atom that has the lower electronegativity. This one is then going to become positive, and the one that has the higher electronegativity is going to become negative by gaining that electron. And we'll use sodium and chlorine as an example. Now, sodium is a metal. It's on the left side of the table in group 1, and it has an electronegativity of 0.9. Chlorine in group 17 on the right side of the table is a nonmetal. It's to the right of the staircase and has an electronegativity of 3.2. Now, to find the difference, the END, the electronegativity difference, we subtract those two, 3.2 minus 0.9, and we get a value of 2.3. This value is above 1.7, which tells us that the bond between sodium and chlorine is going to be ionic. And in general, metals and nonmetals are always going to have an ionic bond. It's good practice to double check to make sure where the electronegativity difference lies, especially when we consider our other types of bonds, because those ones, it's going to depend on a specific value of electronegativity difference to determine, again, like ionic, what type of bond we actually have. So the sodium loses its valence electron because it doesn't have a very strong attraction for it. it oxidizes and becomes a positive ion, a cation, a sodium +1 cation. That electron doesn't just get lost. The chlorine, since it has a higher attraction for it, takes it and gains it and reduces. So it gains that electron, that's reduction. So chlorine reduces and becomes a chlorine -1 ion, an anion. So since these two ions are oppositely charged, we have a positive and a negative, kind of thinking like opposite ends of a magnet. They're going to attract to each other and form the ionic bond that holds together sodium and chlorine in the compound sodium chloride. Now we can take that sodium chloride compound and dissolve it into water, which will also break the bond. This causes that compound to separate into positive and negative ions, which will be attracted to which we'll learn about, polar water, which also has a positive and negative end, that's going to dissolve them. So something as simple as dissolving is strong enough of a process to break the bond between the sodium and the chlorine. And what we end up with are these ions floating around in our solution. These positively and negatively charged ions floating around in our solution. Now a little pictorial representation of what's actually happening here with ionic bonding between sodium and chlorine. Now on the top we have a neutral sodium atom and a neutral chlorine atom. And we can see that in the outer valence shell of chlorine, there is one missing spot for an electron. And in the outer shell of sodium, we only have one electron. So looking at our configurations here, this is going to be, in order to get a stable octet, as sodium loses this one, it can have a stable octet in its second level. And if chlorine gains one, then it can have its stable octet filled in its outer level. And this is desirable by both parties. This is a win-win for each of those atoms. Sodium becomes a more stable ion, losing its outer electron, and the same thing happens with chlorine. This leaves the sodium with an overall +1 charge and an overall -1 charge for the chlorine. These two oppositely charged particles, the anion and the cation, are attracted to each other, and that's our ionic bond. Now this is important to note, a few ionic compound properties which would be pretty consistent for any ionic compound. Generally we use salt, table salt, as the example. So sodium chloride, like all ionic compounds, are going to have high melting and high boiling points. For example, sodium chloride melts at a temperature of 1074 Kelvin. Now if we think about that in terms of Celsius and we add 273 to that, we're looking at something like 1300 degrees Celsius. That's not really something that you can obtain by your stove or your oven or anything in your home, really. It's one of the reasons why salt is used in the kitchen for a lot of various different things, especially cleaning as an abrasive, because it doesn't melt. It stays as a solid form at high temperatures, which has certain advantages in certain situations. Ionic compounds also have low vapor pressures, which means that they don't evaporate easily. There's not a lot of pressure being essentially put off by the atoms at the surface that are turning into gases, which means that we have a low vapor pressure. So a salt is not going to turn into a gas just sitting there at room temperature. It's going to require an input of energy in order to actually get those atoms moving with enough energy in order to melt and evaporate. Ionic compounds are also very brittle. Salt does crush easily into a powder. We can put it into a mortar and pestle and grind it down pretty easily. Ionic liquids and solutions. So whether this is sodium chloride, and we'll see this sodium chloride as a liquid, so that's the compound in liquid form, or sodium chloride dissolved in water, which is an aqueous form, and those are very different things. One of these we can find in the ocean. This one is highly reactive, as we have halogens and group 1 metals that, when they're in their liquid phase, are extremely reactive. But these solutions, or ionic liquids themselves in the liquid phase, are considered electrolytes. And electrolytes mean that the resulting solution conducts electricity, because the charged particles that are contained inside that solution or inside the ionic liquid are free to move around and carry their electrical charge from one place to another. So they allow the free movement of electrons, which is essentially electricity. So if we have an ionic liquid or a solution that has an ionic compound dissolved in it, it will conduct electricity. But we'll find that if the substance is not ionic and it doesn't separate into charged particles, it will not conduct electricity. So the key here is that we have freely moving charged particles, and that's what's going to constitute an electrolyte. Now, for example, ionic solids in the solid phase do not conduct electricity because the ions are held together in the crystal lattice. They're not free to move around each other and transfer those electrons from one place to another. We'd have to either dissolve it into water, or we'd have to melt it into the liquid phase in order to get that ionic solid to conduct electricity. Now, just as a side note here, in the solid ionic crystal, the ions are locked in place. Again, unable to move around, unable to conduct electricity. So this is why the ionic solids can't conduct electricity. But once those ions are broken up and separated by adding heat or dissolving into water, the ions are now free to move around. And if we were to place wires connected to a source of electricity like a battery into the water, the ions will carry the electrical charge from one wire to the other, allowing the electric current to keep flowing. It's essentially like placing a piece of metal in between two wires to complete a circuit. The liquid with the freely moving charged particles in it will conduct electricity just the same as metal would. And we'll learn more about that in a later lesson. Now, the last thing that we'll spend some time on with today, which is a little bit of a review, is ionic bonding dot diagrams. And we'll review anions and cations, and then we'll see what they look like when we put them together into a compound. Now, remember, when we write these anion dot diagrams for, this would be for nonmetals, because nonmetals tend to create negative ions. They gain valence electrons to make a stable octet and fill their valence shell. So we write the dot diagrams for any anion, for any negative ion, with brackets around the symbol and 8 dots around the symbol to indicate that that atom has, or that ion has filled its valence shell with 8 electrons. And then we write in the upper right hand corner how many electrons that ion gained in order to attain the charge that it has. So oxygen gains 2 electrons in its valence shell, so therefore it has an overall charge on its anion of -2. And again, that's going to indicate the number of electrons that were gained. When we write our cations, the metals lose valence electrons to make their stable octet and become cations, positive ions, and now has 0 electrons in what was the valence shell. Now, to write the dot diagram of the metal ion, we're going to do it just like the anion. We're going to write its symbol, but instead of putting all the dots around it, we're going to put 0 dots around it. And that's to show that what was the valence shell lost all of its electrons. And then, depending on how many it lost, we put that number with a positive sign indicating that they were lost in the upper right-hand corner. So we see that the positive ions get 0 dots around the symbol, and the negative ions get 8 dots around the symbol. Then we add in our brackets to indicate the ion and the overall charge in the upper right-hand corner of that ion. Now, when we put these dot diagrams of ions together to show a compound, we want to draw the dot diagram in a way that accomplishes a couple things. we arrange them in such a way that the ion charges cancel out and add up to 0. So we're going to have things like a +1 and a -1. We want to make sure that those charges add up to 0, given the different types of ions and their charges. The opposite charged ions are next to each other, and the like charged ions we want to try and put as far away from each other as they can be. Remember, because opposites are going to attract and like charges are going to repel. So for example, lithium fluoride. We have a metal and we have a nonmetal. So we have a +1 and a -1 ion. These charges are going to add up to 0, and they're as far apart as they can be. No matter what orientation we put them in, they're going to be as far apart from each other as they possibly can. And this looks a little bit differently once we get more ions in our formula. For example, BeF2, beryllium fluoride, has 1 positive ion and 2 negative ions. And if we look at beryllium on the table, it does like to produce a +2 cation. And in order to get this to add up to 0, we're going to need 2 -1 fluorines. Because +2 -1 would be 1, -1 would be 0. And we're going to write this like this because this is going to give us the fluorines as far away from each other as we can get them, as opposed to writing something, I'm just going to do the shorthand real quick, something at maybe 12 o'clock and 9 o'clock, right angles to each other. This is not separating the like charges, the fluorines, as far away from each other as we can. That's why we put these over here at 180 degrees to separate them as much as we can. Now we'll get into some more different types of bonding in our next lesson. And for now, we'll focus on ionic bonding, and remember that this is determined by determining the electronegativity difference between competing atoms that are involved in a chemical bond. If you guys have any questions, make sure you come see me to get your questions answered. Have a great day.